Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to derive an expression for the power spectral density of non-return to zero bipolar format. We know that in an NRZ bipolar format, a symbol 1 is represented by alternatingly transmitting a pulse of amplitude plus A or amplitude minus A for a duration of 1 TB, whereas symbol 0 is represented by turning off the transmitter for a duration of 1 TB. The power spectral density of a discrete PAM signal x of t is given by the formula Sx of f equals 1 by TB magnitude square of V of f summation n varying from minus infinity to plus infinity Ra of n into exponential of minus j 2 pi n f capital T, where TB is the bit duration, V of f is the Fourier transform of the basic pulse V of t, and lastly Ra of n represents the autocorrelation function of the input signal x of t. Right. To start the derivation, we note that a bipolar format has three amplitude levels, plus A, 0 and minus A. We note that plus A and minus A represent the amplitudes of the positive pulse as well as the negative pulse that are used to represent symbol 1, whereas 0 represents symbol 0. Let us start by saying that the zeros and ones of some random binary sequence occur with equal probability. That means the probability of occurrence of symbol 0 equal to probability of occurrence of symbol 1. Now, since we have symbol 1 representing two amplitudes alternatively, that is A as well as minus A, we now note that probability of amplitude of symbol K, which is AK equals to A, equals to 1 by 4. Very similarly, probability of AK equals to minus A is also equals to 1 by 4. Now these two combined together represent symbol 1 because we have a positive and negative pulse representing symbol 1. And lastly, probability of AK equals to 0 is equal to 1 by 2. Now when you add all of them together, we will obtain a probability of amplitude AK equals to 1. So here we note that probability of occurrence of symbol 0 is 1 by 2 and probability of occurrence of symbol 1 combining both positive as well as negative pulses is also equal to 1 by 2. Let us now start by finding the autocorrelation function Ra of n first, and the formula for autocorrelation function is given by expectation on Ak into A of k minus n. Let us start by assuming n equal to 0. Now when I substitute n is equals to 0 here, I will have expectation of Ak into A of k minus n become Ak A of k minus 0, which is Ak itself. So it will reduce to expectation on Ak square. Let us now substitute the values of the amplitudes. Please note we have three amplitudes, plus A, minus A as well as 0. We'll start with plus A here. We have amplitude whole square multiplied by the probability of occurrence of the corresponding amplitude. Now the first amplitude is A, so we have A whole square into probability of AK is equals to A, plus the second amplitude is minus A, so we have minus A whole square into probability of occurrence of minus A, and lastly we have the third amplitude 0, so it is 0 whole square into probability of occurrence of symbol 0. Now from our previous expressions we have probability of AK is equals to A is 1 by 4, AK is equals to minus A is also 1 by 4, and lastly probability of AK is equals to 0 is 1 by 2. Let us now substitute these values into our equation. So it will be A whole square multiplied by 1 by 4 plus minus A whole square multiplied by 1 by 4 again, and lastly 0 square multiplied by 1 by 2. This time anyhow will cancel out. So what we will have is A square into 1 by 4 plus minus A whole square into 1 by 4. So this will reduce to plus A square by 2. So the autocorrelation function for the bipolar format when n is equals to 0 is A square by 2. Now let us consider the next condition, that is when n is equals to 1. Coming back and substitute n is equals to 1 here, we will have Ak into A of k minus 1. So now we have a 2-bit combination and the combinations are shown in the table here. Please note this is a 2 combination table, so we will start from 0, 0 and 1, 1. Wherever 0 is there, we replace it by 0, and wherever we have a 1, we have to replace it by A, and if there are two 1s consecutively, the second one has to be represented by minus A. So 0, 0 is written as 0, 0 itself, 0, 1 becomes 0 A, 1 0 will become A0 and 1 1 has to be written as A and minus A. So the product of these terms are 0 multiplied by 0 is 0. Then we have 0A is 0. A0 is also 0. Finally, A multiplied by minus A is minus A square. Now we assume that these successive symbols in the binary sequence are statistically independent and therefore they will occur with equal probability. Now since there are 4 symbols, the probability of occurrence of each symbol will be 1 by 4. That is what is written here. So now let us substitute these values into our autocorrelation function. So expectation on ak into a of k minus n equals, since symbol 0 appears 3 times, we will write it as 3 multiplied by the symbol value which is 0 multiplied by the probability of each of the symbol value which is 1 by 4 plus the last symbol which is minus a square multiplied by its probability of occurrence which is 1 by 4. So this term will reduce to 0. Therefore, what we will have is minus a square by 4. This is the autocorrelation function for n is equals to 1. Now, for a very similar approximation, when I consider n is equals to minus 1, we will again have the autocorrelation equal to minus a square by 4. So now I can write the autocorrelation function for the bipolar format when n is equals to plus or minus 1 is equal to minus a square by 4. Lastly, we now consider the remaining values, that is n greater than 1. Now for n greater than 1, the obvious choice for the product ak and a of k minus n will have a minimum at ak and a of k minus 2. So since I have a of k minus 2 considered, I have to consider a of k minus 1 value as well. Therefore, now we will have a 3-bit combination table starting from 0 0 0 till 1 1 1. Now you have to be very careful when representing the amplitudes here. Wherever you expect a 0, you can put a 0 as it is. But wherever you expect a 1, and if the corresponding combination has only 1 1, then that is to be represented as A. And if on the other hand, the combination has 2 1s, then the second one must always be represented by minus A. So you can see 0 0 0 is as it is, 0 0 1 is 0 0 A. But here, the fourth combination, we have 0 1 1. So the first time the 1 appears, it has to be put as plus A. The second time it appears in the same combination, it has to be put as minus A. So in the very similar fashion, you have to fill up the remainder of the table. The last combination is 1 1 1. So the first one is plus A, second one is minus A, the third one is again plus A, and this is how you construct the table. Now let us go for the product term. You have to note the product term is ak and a of k minus n. So I have to only multiply the values in the first column and the third column. So 0 0 is 0, 0a is 0, 0 0 is again 0, 0 multiplied by minus a is also 0, a0 is 0. Coming to this term, we have a multiplied by minus a, it is minus a square. Then we have a and 0, it is 0. Lastly, we have plus a and plus a, so it will be plus a square. So now we have 8 symbols. Once again, we assume that the successive symbols of the binary sequence are statistically independent. Therefore, they will have a probability equal to 1 by 8 each. Here, I have mistakenly given it as 1 by 4. Please make that correction. This should be 1 by 8. Now, let us substitute these values into the autocorrelation equation, which is expectation on ak into a of k minus n. Now, we see that the symbol 0 appears 6 times. So, I will write it as 6 multiplied by the symbol value, which is 0, multiplied by the probability of its occurrence, which is 1 by 8. Then we have a plus. A square appears 1, so it will be 1 multiplied by a square multiplied by 1 by 8. And lastly, we have minus a square appearing once again. So it will be 1 multiplied by minus a square multiplied by 1 by 8. So when I take the summation, I will note this is 0. This is plus a square by 8. This is minus a square by 8. So the overall summation will result in a 0. Now we will write all of these values for the autocorrelation in one single expression, which is Ra of n equals to, for n is equals to 0, it is a squared by 2. When n is equals to plus or minus 1, we have minus a squared by 4. And lastly, when n is greater than 1, Ra of n is 0. Right. So with that, we have completed the computation of the autocorrelation part. Let us now move on to find V of f. We know that V of f is the Fourier transform of the basic pulse, and we already have stated the shape of the basic pulse is rectangular in nature. Let us go back to that term now. Right. So we now state the basic pulse V of t is a rectangular pulse of unit amplitude and duration 1 TB. So you can see we have minus t by 2 and plus t by 2. So the difference between them is capital T. Here we have taken the value of t as 1 TB. Now, since it is a rectangular pulse, the Fourier transform of the rectangular function is the sinc function. So this represents the Fourier domain representation of the basic pulse v of t. Now you can see here this is a representation for v of t in the Fourier domain, which is given by a capital T sine of pi capital Tf divided by pi capital Tf. Now since we have considered a unit amplitude pulse, capital A is equals to 1, t is Tb here. Then we have the last term, that is sine pi Tf divided by pi Tf, reduces to sinc of t into f, because sine of pi x divided by pi x is sinc of x. So the final expression for the Fourier transform of v of t is given by equation 6 here, which is Tb sinc f Tb. Right. With that, we have now found both the Fourier transform of v of t as well as the autocorrelation function. So let us now go and substitute that into the power spectral density equation, which is again given here for convenience. The expression says S6 of f is equals to 1 by Tb magnitude square of v of f, summation n varying from minus infinity to plus infinity, Ra of n into exponential of minus j2 pi nf capital T. Let us start by substituting for v of f, which is Tb sinc f Tb. Then we have magnitude as well as square applied. Then we have the summation term, and the remainder of the term is as it is. Let us simplify this part first. This will simplify to Tb square sinc square f Tb. We already have a Tb here, and there is a Tb square, so they cancel to produce 1 Tb followed by sinc square f Tb. Now let us come to the autocorrelation function. Since we have autocorrelation computed for 4 values, please note 0, plus 1, minus 1, and lastly n greater than 1. So we have to now split this part into 4 parts. One is for n is equals to 0, then we have n is equals to 1, n is equals to minus 1, and lastly n greater than 1. So the first part is Ra of 0 into exponential of 0, because n is assumed to be 0 here. Then the second one is Ra of 1 into exponential of minus j2 pi ft, because n is 1. Now the third one is substituted by assuming n is equals to minus 1. So it will be Ra of minus 1 into exponential of j2 pi f capital T. We know there is a plus here. And lastly, we have summation n varying from minus infinity to plus infinity, and n not equal to 0 as well as plus or minus 1. Ra of n into exponential of minus j2 pi n f capital T. Now, going back to the equation for autocorrelation and noting that for n greater than 1, Ra of n is 0. When I simplify this part, this will reduce to 0. Let us come back to this part. This is Ra of 0 into exponential of 0 is 1. So it will only be Ra of 0. The remaining 2 terms remain as it is. Now let us substitute for these Ra of 0, 1 as well as minus 1 values, which is done here. Ra of 0 is a squared by 2. Ra of plus 1 is minus a squared by 4. Ra of minus 1 is also minus a squared by 4. So we have a squared by 2 plus minus a squared by 4 into exponential of minus j2 pi f capital T plus minus a squared by 4 into exponential of plus j2 pi f capital T. Now let us take minus a squared by 4 as common term here. So what remains is exponential of minus j2 pi ft plus exponential of plus j2 pi ft. Now looking into this term, you note that this is in the form of e to the power of minus theta plus e to the power of plus theta. If I rewrite it as e to the power of plus theta plus e to the power of minus theta, this will simplify to 2 cos theta. So this complete term will reduce to 2 into cos 2 pi ftb. Right. So now you see we have a 4 in the denominator and a 2 in the numerator. They cancel to produce a squared by 2. Then we will take a squared by 2 as common. Now when I take it outside toward the constant term, it will be a square tb divided by 2. Then followed by sin square ftb as it is. So what remains inside is 1 minus of cos 2 pi ftb. Again, by applying the trigonometric function and noting that 1 minus cos 2 theta is 2 into sin square theta, we'll simplify this part to 2 sin square pi ftb. Now, we have a 2 in the denominator here and we have a 2 in the numerator here. Let us cancel them out, and this produces the final expression for the power spectral density of bipolar format, particularly NRZ type, as a squared Tb sin square ftb followed by sine squared pi FTB. Now let us have a look at the normalized form of equation A. Right. Here we are searching for the bipolar, which is given by a blue colored waveform. This is the one. So you see, this is the normalized form of the power spectral density of the bipolar format. Right. With that, we come to the end of this discussion on the derivation for the power spectral density of NRZ bipolar format. If you like this video, kindly press that like button and subscribe to my channel for more videos on digital communication. Thank you for watching. Have a good day.